In this lecture, we will discuss another popular data-driven data mining technique called naive Bayes. The technique is based on the Bayesian classifier, which was developed by Reverend Thomas Bayes about 300 years ago. As you can see, the concept of many of the data mining techniques were actually conceived a long time ago, but it was the modern computer technology that made the implementation of these techniques feasible and efficient. Just like KNN, naive Bayes is a data-driven technique which shares the same pros and cons of other data-driven techniques. Its effectiveness would depend on the existence of a large data set and can be useful in dealing with data sets where a clear pattern or relationship does not exist. At the same time, it offers a somewhat black box solution, making interpretation of the model difficult. To understand naive Bayes technique, you need to first develop some Bayesian thinking. So what is Bayesian thinking? Well, let me give you an example. At a campus party, you meet Tom. When Tom talks with you, he looks at his shoes. Needless to say, Tom is quite shy. Let me ask you this question. Without knowing anything about Tom, do you think Tom is a math graduate student or Tom is a business student? Based on my past experience asking students about this question, you are likely to say that Tom is a math graduate student. Is that right? After all, there is a joke about mathematicians that says, how do you know if a mathematician is an extrovert? Well, he or she looks at the other person's shoes when he or she talks, instead of looking at his or her own shoes. Nevertheless, is Tom really a math major? Well, instead of relying on the stereotype of mathematicians, we need to think differently. First, what do you think is the ratio between number of math graduate students and the number of business students on campus? Well, a conservative estimation would tell me that it is probably at least 1 to 9, meaning that for each math graduate student, there are at least 9 business students on campus, because business students is a much larger population. So if we put all math graduate students and the business students together in this box, about 10% would be math graduate students and 90% would be business students. Now, what percentage of math students would you say that are shy? Would a high percentage such as 75% do it? Well, let's shade the portion of math graduate students that are shy on this diagram. What percentage of business students would you say are shy? Well, how about a low percentage such as 10%? Well, let's shade that portion on the diagram as well. So the first one, which is the percentage of math graduate students who are shy, is 75% of 10% of the total population, which is 75% multiplied by 10%, or 7.5% of the entire population. The second shaded area, which has the shy business students, is the 10% of the 90% of the entire population, which is 10% multiplied by 90%, or equal to 9% of the total population. So as you can see here, from a probability perspective, Tom is actually more likely to be a business student than a math graduate student. So this is what I mean by Bayesian thinking. Instead of making predictions based on intuition or stereotype, we base our prediction on probability analysis. The example I just discussed is relevant to an important concept in statistics and data mining called conditional probability. Conditional probability is defined as the probability of event A given that event B has occurred, denoted P A bar B. For example, the probability of applying for a home equity loan given that the bank customer has an income of over $75,000, or the probability of making a purchase given that the potential customer owns a house. In the previous example, we are looking for the conditional probability of Tom being a math graduate student given that Tom is shy, or Tom being a business student given that Tom is shy. And then we can write the conditional probability like this. The concept of conditional probability is central to the Bayesian classifier, which searches the conditional probability of the case belonging to the target class given the predictor variables have the values of x1, x2, and etc. Since we are often more interested in the target class, that's why we tend to compute the probability of the case belonging to the target class. Nevertheless, you can use a similar notion to indicate the conditional probability of the case belonging to the non-target class for the Bayesian classifier like this. One interesting feature of naive Bayes technique is that it is a supervised data mining technique for classification with categorical predictor variables. This suggests that when using naive Bayes, both target variable and the predictor variables must be categorical. You may be thinking that this sounds quite limiting. Not so. Remember that in the business context, classification is the predominant type of problems that we face, and we often deal with a lot of categorical variables such as sex, education level, or day of the week, and so on. In addition, numeric variables can be easily transformed to categorical variables through binning. As a technique that is designed to work with categorical variables, naive Bayes also presents some unique advantages. First, it does not require the transformation of categorical variables into dummy variables or category scores, as in some other data mining techniques, which helps maintain the integrity of the data in its original forms. Second, it lends itself to some unique problems that cannot be easily solved using other techniques. For example, email spam blockers. This is a very common application you use every day. The way a spam blocker works is to compute the probability of an email being a spam email given the presence of a list of keywords and characteristics that exist in the email. The probability values are calculated using a large body or corpus of emails that have been classified manually into the spam and the no spam categories. And a naive Bayes is the perfect technique for those applications, as all predictor variables are categorical, indicating whether a keyword or characteristic exists in the email. Therefore, naive Bayes is a technique that greatly complements other data mining techniques so that you have the ammunition to attack a wide range of data mining problems. Now let's first look at how the Bayesian classifier works by looking at an example. In our example in this slide, we are trying to develop a model to classify potential customers into the purchase and the no purchase groups by using the variable of sex. The table in the slide shows that among the current male customers, 30 of them purchased, while 20 did not purchase. Among the female customers, 50 of them purchased, while 100 did not purchase. It is helpful if we know the total number of male and female customers and the total number of purchasers and non-purchasers. So, if you add the numbers up, there are a total of 50 male customers and 150 female customers. And there are a total of 80 purchasers and 120 non-purchasers in the dataset. And if you add all the numbers up, there are a total of 200 cases in the dataset. How do we find out the probability of a customer belonging to the purchase class, which is the target class that we are interested in, given that the customer is male? And likewise, what is the probability if the customer is female? Well, the Bayesian classifier suggests that we are looking for the conditional probability of y equal to 1 given x equal to 1, which is male, and the conditional probability of y equal to 1 given x equal to 0, which is female. To find out the first conditional probability, we realize from the table that 30 out of the 50 male customers purchased, providing a conditional probability of 30 divided by 50, or 0.6. Similarly, we find that 50 out of 150 female customers purchased, providing a conditional probability of 50 over 150, or 0.333. If we use the default cutoff rate of 0.5 for a binary class problem as the cutoff value for this problem, we would classify all future male customers into the purchase class and all future female customers into the no purchase class. If we use a sliding cutoff rate with the overall probability of purchasing, which is 80 out of 200 cases, or 0.4 as the cutoff value, we still would classify all future male customers into the purchase class and all female customers into the no purchase class. The strategic implication of this finding is that we should focus our future marketing efforts on targeting male customers as they have a higher probability of purchasing the product. As you can see from this example, the Bayesian classifier is quite simple to understand and compute if you have only one predictor variable. But as the number of variables increase, things can get much more complicated. The previous example shows how the Bayesian classifier works, and it also illustrates a couple of important requirements of the Bayesian classifier. First, it requires other cases to have exactly the same predictor values as the case to be classified. For example, if we want to classify a customer who is male, we need to find all existing cases where the sex of the customers is male. In other words, only the cases that have the exact same predictor values as the case to be classified will be used in this analysis. This kind of explains the second requirement of the Bayesian classifier, which requires the predictor variables to be categorical. The reason for that is because numeric variables would have too many possible values, whereas categorical variables have only a limited number of categories. When we have numeric predictor variables such as income and age, we can simply transform them into income and age categories, which limits the number of possible values for these variables. However, even with categorical variables, it can be difficult to find exact cases when you have too many variables. For example, if we are trying to classify a case with income in income category 2, age in age category 3, sex equals to male, and college education equals to yes, that would eliminate a lot of cases that do not match all the predictor values in the dataset from the computation of the conditional probability. Theoretically, for a categorical variable with 5 equally frequent categories, would reduce the likelihood of finding a match in the training dataset by a factor of 5. And 2 such variable would reduce the likelihood by a factor of 5 squared, or 25, 3 by 5 cubed, or 125. If you do the calculation, having 10 such variables would make the probability of finding an exact case in the dataset almost 1 in 10 million. This makes the Bayesian classifier not very practical in the real world. So later in this lecture, we will talk about the naive Bayes technique, which is an extension of the Bayesian classifier that makes the technique more feasible to a wide range of real-life business problems.